Okay, here we are, 8-2, and we're going to spend 2 days here. On this first day, we're going to be analyzing graphs and looking at a function, its derivative, and the second derivative. So first of all, we want to talk about critical points. Critical points on a function happen when the derivative is 0, and when does the derivative equal 0? You should know a couple of these. Remember, we get a 0 derivative when there is a max or min on the original function, and also one that we haven't talked about is when there's a horizontal plateau. So a max, a min, or a horizontal plateau. And I'll show you one of those in a minute. So that's the only time the derivative is going to equal 0, at a max, a min, or horizontal plateau. So there will be, obviously, those are 3 critical points. Critical points also happen when the derivative is undefined. Okay, and when the derivative is undefined, the author is now, instead of calling it undefined, he's calling it an infinite derivative, infinity. So when does the derivative come up undefined or equal to infinity? That happens at, and you know one of these, a cusp, and one you don't know is a vertical plateau. So there's 2 spots where the derivative is undefined, cusp or vertical plateau. On a continuous graph, obviously at a vertical asymptote too, but we're not talking that. We're talking continuous functions. So let's look at a couple of graphs to pick out what's going on. We're going to look at 3 distance time graphs. Distance and time. So we've got a car that stopped, takes off, pauses, then takes off again. Get rid of that. Okay, so here's our car. Takes off, slows down, stops for a bit, then takes off again, speeds up. So what we've got right in here where it stopped and paused is called a horizontal plateau. So that's our only critical point on this graph. And if we think about if we think about the derivative now, let's call this f of x. If we were going to do a rough sketch for the derivative, remember, all we care about is whether the original function is increasing or decreasing. Here it's increasing, and so that means the derivative is all positive values. Well, here's my derivative is 0. So my derivative for this part of the x-axis has all positive values. And here it's increasing again, so it's still all positive. What we basically did was go from a cubic function to a quadratic function. And you know that exponent decreases by 1. But this is what the derivative graph would look like. Okay, the next one. Okay, I'm standing and you travel in the car, and we're going to look at the distance of you from me. So we're going to start this far away from me. You're going to take off, so you increase your distance from me. Then you decide you miss me, so you're going to turn around and come back. So your distance back to me decreases. So we basically have an upside down parabola. We have this critical point here. This critical point would be a max. Here was our horizontal plateau. Here's our max. I know at the critical point, this is f of x. I'm going to do a rough sketch for f prime of x, the derivative. This is going to be 0. Here my graph is increasing, so I know my derivative is positive. And if I think about a quadratic equation, that's to the second power. When I know when I take the derivative, I'm going down to the first power, and anything to the first power is linear. So I know that these values, whatever angle it's at, it's linear. After my critical point, I'm decreasing, which means all of my derivative values are going to be below the x-axis. And I get that. So I get this nice linear function for the derivative. And the last one, I don't have a story for, but that's okay. I'm going to go with an absolute value graph. Okay. Here we've got cusp, which is a critical point. It's a cusp. We know that the derivative is undefined here. There's not going to be a value on the derivative. So I do have two parts. Here I am decreasing, and it's linear. And I know the derivative of a linear function equals the slope. So this is some negative value. So my derivative would be a constant negative value. But when I get to this point, it's going to have an open circle because I know there's no value. It's undefined. Then here, I'm increasing again, so my derivative function jumps up here, open circle, all positives at a constant rate. So the derivative would be a piecewise graph. Okay, some definitions. You're not going to have to do all this stuff. Well, forget I said that. Just some vocab coming next. We want to talk about an absolute, also known as a global max or min. This, if it was a global max or a global min, a global max would be the highest point for the entire graph. The min would be the lowest point for the entire graph. So it's the highest or lowest if it's a min. Point on the graph. And we can talk about relative or local max or mins. So here, these are the highest or lowest. Point for a given interval. So a graph to explain these. Okay, I'm going to chunk this up from A to B to C to D to E. Okay. And what I did was I picked an interval where I'd have a critical point all the way through here. From A to B, I can see the critical point is this maximum right here. And this would be considered a relative max because it's not the highest point on the entire graph. It's just the highest point in this interval from A to B. So from A to B, this would be my relative max. from C to D, oh, I forgot this, B to C, I've got a relative min because I've got points that go lower than that on both edges here. So this is a relative min. It's a minimum in this given interval from B to C. In this interval from C to D, I've got a max. And because this is the highest point for the entire function, this is a global max or an absolute max, whichever one you want to call it. Then I picked an interval from D to E. Nothing really special going on in here. So if I was to say what's going on in here, well, each endpoint is a critical point here. For this interval from D to E, this would be a relative max, because it's the highest point on the interval, and this would be a relative min, because it's the lowest point on this interval from D to E. All I'm looking at is this part of the graph. Nothing in the middle is interesting, it's at the endpoints that's interesting. So, if it's the highest point for the entire function, it's the global or absolute. If it's just a high or low for the given interval, then it's the relative. Okay. Now, when does a relative max occur? Or global max for that. So a relative, I'll just say max. A maximum occurs when the derivative changes from positive to negative. You will have a maximum. So let's just take a look and see. So if I had a parabola, I know this is my critical point, the derivative is 0 here. All of these values, because the graph is increasing, I know that all of my derivatives are going to be positive. When I get to here, the derivative is 0. But then after here, now I'm decreasing, all of my derivatives go to negatives all the way down, because it's decreasing. So when it goes from positive to negative, I know I'm going to have a max. So it's the slope of the tangent lines, remember, that we're talking about here. The slope of the tangent lines are all positive because they're all going uphill. After this, they're all going to be going downhill. So what does that mean? When is a minimum going to occur? A minimum occurs when the derivative changes from, and think about it, what's it going to take to have a minimum? The derivative is going to change from negative to positive at the critical point. And let's take a look. So let me put a minimum in here. There's my critical point. I know the tangent line, the slope is 0 because it's horizontal. Here, all of my tangent lines are going to be downhill, so they're all going to have a negative slope. After the 0, now my tangent lines are going to be going uphill. They're all switching to positive. So when the derivative goes from negative to positive, you're going to have a minimum. Okay, those are pretty straightforward. Now those plateau points. You will get a plateau, either vertical or horizontal. Plateau occurs